I don't really know why Canvas is acting up other than, hey, it's Canvas, but, let me see if that, okay, that one is where I expected it to be on the announcements page. Okay. So at 2:05, it should send out an email. Let me just check my email really quickly. Wow, yeah, I only got the one that was sent from my blueprint. So that's really weird. Okay. I have not looked at my email today because I am running a little bit behind today. So if you sent me a question before class, I haven't gotten to it. It looks like there's a lot of questions, so I'm going to answer those after class when I have time. In the meantime, today we are going to do units 4 and 5, which are actually really short, so today's lecture is probably not going to be that long. And then we just fill it with questions and more Q&A afterward if you guys want, or we call it a day early, I don't know, whatever. The workbook splits density and temperature into 2 separate sections. I don't really know why temperature needs its own unit, because it's literally going to be one slide where I give you some formulas and then we use them. And I'll talk about absolute zero for a bit because it's interesting. But density is much more important. And basically, the premise behind density is we can split it up into 2 applications. One is what is density, so we'll have to define it. And then 2, how do we use density to solve problems? And that answer to that is, well, we treat it like a conversion factor, because it's a relationship between mass and volume. Pardon me while I drink some more water here. Okay, hopefully people will be getting that email shortly, because my clock just ticked over to 2:05. Did the announcement post this time? I haven't seen it yet. We'll see if Canvas spits out an email in a second. This is OLA, so let me see if it's posted on 2:05. Okay, so presumably an email has gone out. Oh, there it is. I just got it. Okay, cool. Excuse me. Okay, so students will start to funnel in if they are relying on the emails. And again, I apologize for the delay in getting the stream running. Yeah, so we'll get started here. Let's talk a little bit about what density is. Density is defined as the ratio of an object's mass to whatever space it takes up. So that's shown right here. The density D, oops, that's not my pen, will be related to mass divided by volume. Now, mass is always going to be in grams for the purposes of density in chemistry. If you go into physics, you can do density in grams or kilograms. It doesn't really matter which of those you choose, but the volume is going to be linked to it. In chemistry, our volume will be either cubic centimeters, milliliters, or liters, depending on what state the matter is in, to give us numbers that are nice to work with. So I'm not working with something like, oh, it has a density of 0.0000004 kilograms per cubic meter, or whatever. So on the bottom, you can see that I accidentally popped up the slide here, but solids generally are represented with densities that have grams per cubic centimeter because you can make a cube out of a solid pretty trivially. Liquids, on the other hand, are very hard to make into solids unless you pour them into solid, like frames or containers or something. Or rectangular frames, I should say. So instead, we measure liquids in milliliters because a cubic centimeter and a milliliter are exactly the same thing. So in general, solids and liquids tend to have roughly similar densities, like within an order of magnitude. Now, obviously, solids are more dense. Like if you pick up a chunk of, say, iron, and you pick up a bucket of water, those are going to have comparable densities. The exception would be mercury, which is a liquid and is extremely dense. If you ever carried a gallon of mercury, what the hell are you doing, first of all, because you should not have access to that much mercury. But in the event that you have, and I have because I worked in a laboratory where we use mercury to like put in in a barometer, it's really, really freaking heavy. So most solids will have densities higher than those of liquids, but there are some exceptions that exist. And also, yeah, you'd be going crazy, because that's what mercury vapor does to you. Finally, the last one, gases are measured in grams per liter, and the reason for this is just out of convenience. You could express grams per milliliter for gases, but you'd end up with a number that's like 0.0001. If we change the volume to liters, then we actually get about a gram of stuff, depending on the material you're looking at, like hydrogen or helium or whatever. And thus, we have a number that we can work with. Okay, so those are the units. I'm going to try and stick to those units for the problems that we're doing. Whenever I write a density, obviously you're going to write units with the density, so you're not going to have to rely on, oh, it's a gas. Crap, what was that? Because I don't write the units. No, I will write the units. And for what it's worth, we don't really deal with gases much in 160 or 140. We'll do that in 160. Sitting here doing the chapters in my head. 162 is when I believe we do gases. It's been moved around a lot. All right. Now, if you mix any two things together, they tend to organize themselves by density. So if I had, like, say, a bin of water... Oops, that's... Well, I guess I could do this. There we go. There's my bin of water. It's held in glass, which you can't see. So that's fine. And I'm going to put in my bin of water, I'm going to put something... I don't know, I'll put this block. And here's what the block does. So this is block A. And then I'll put in block B. And block B falls down here. It's really hard drawing in 3D when you can't see what's on what you're drawing. Okay, so that's B. And this is just water. Colored baby oil with water. I don't know what baby oil you're using, but deep sea blue is not exactly the highest choice on my list here. Anyway, if I asked you, hey, which of these is the most dense, or arrange them in the order of their density, well, you would say, okay, the one that sunk to the bottom had the highest density, so largest to smallest density would be B. We know that A is less dense than B because it floated, but more importantly, A is floating on top of the water. So, not only is A a greater density than B, or I'm sorry, A is less dense than B, the water can be placed in there too. You don't like my container? My container that looks like this? There we go. There's my container. So you can always sort stuff by their density based on how it arranges itself in a column. In fact, in one of the videos I have right here, which I just drew over, it's beautiful. Thank you. I appreciate it. Yeah, this is the premise behind a Galileo thermometer, is we put a bunch of different substances in there that expand when you heat them. And as they expand, their density decreases, and they float to the top. Yeah, I have no idea what I was drawing, but now you can't actually see the link that I'm posting. But this is going to be a demo of a density column with household materials. So let's put this on the screen here. And give me a second so I can set it up here. Window capture. Yeah, that's the one I want. Boop. That's not quite right. Okay. Okay, I'm going to turn the music down just a little bit. And here, we'll hit play here. So here's all the materials that are going to be used in this. And there's a lot of materials, and most of them are liquids. But some of them are actually solids, which we're going to drop in later to try and figure out where their density falls. And you don't need adult supervision for this, unless you, like, drink the rubbing alcohol. Like, don't do that, obviously. Here's all the liquids. I'm just going to pause real quick. These are liquids that are arranged in both order of density. So honey is the most dense and lamp oil is the least dense. They're also arranged in such a way such that every other layer will mix with each other, and the interstitial layers between those don't mix with each other. So, for example, honey and corn syrup resist mixing as long as you're careful in pouring them. Whereas, like, water and rubbing alcohol will completely mix with each other. But the vegetable oil in the middle prevents them from doing that. Okay? So they're arranged in a very specific way. And as long as you don't actually just stir the stuff, they won't mix appreciably. And we can achieve this density column effect. So we're putting in the liquids. Be careful with 5 exclamation points! But you do have to be careful in order to get the separation, because if a layer goes through the interstitial layer and mixes with the other ones, then they will combine. As you can see here when they drop stuff in there, that there is some mixing that occurs. There you go. So this column has arranged all the liquids on the left and all the solids on the right, and we have sorted them by their density. And so you can see that based on... Oh, Steve is messaging me. That's okay. You can see that based on their position between what liquids. So a ping pong ball is the least dense because it's full of air, obviously. The tomato should be approximately the density of water because tomatoes, like most vegetables and most fruit, are mostly water, but there's extra material in there, so it makes it slightly more dense. So it's sunk below the water level, but is above the dish soap level. The bolt is the most dense because it's metal, so it falls straight to the bottom. And then these other materials are just mixed in here. What did he roll on the die? I don't know. I can't actually see it. He rolled milk. All right, so that's my density column. Not mine, I suppose, but that is a density column that I found online. All right, so let's do an example and figure out what's going to float in this right here. I'm going to have you do this calculation while I attend to why is Steve messaging me 30 times during my lecture. So let's suppose that I have olive oil and water, and I put these quantities in. So the olive oil sample I use has a mass of 18.6 grams and 20 milliliters volume. The water is mass and volume 25 grams and milliliters. First of all, which one will float on top, and then what's the density of each of them? So go ahead and do this very simple calculation for density. We'll go over the answer in just a second. So when you've calculated the density of both of them, type your answer in the chat. And then when I see enough of them, I'll know I can go to the next part. The laboratory video is in the documentation, and you have to click a link to get there. It's unlisted. It's unlisted mostly because it is technically property of EVCC. Because I use their equipment in their space. So I don't want other people to take it, because otherwise I would have to like go through licensing and stuff like that. So look in the lab documentation for lab number 1, and there's like a giant procedure and everything. And in that procedure, it will say, watch the following video, and it'll post a link, and that's the link to the video. And it's on YouTube. It's just that if you try and type it in on YouTube or try and find it that way, you won't find it because it's unlisted. You have to use the link to access it from the document. All right, we're getting some answers here. Yeah, you do need the documentation in order to do the worksheet. So you need both parts. Let's see here. That didn't quite crop correctly. There we go. Okay. So, oops, hold on. Sometimes when I maximize power or Photoshop, it doesn't quite appear. All right, so the density. What color do we want today? Let's do blue. So the density of oil is whatever the mass of oil is divided by its volume. Moil over voil. That's exactly what formula we wanted, right? So the mass we said was 18.6 grams. Make that dot bigger just in case. And its volume was 20 milliliters. When you punch that in your calculator... Oops, I put my calculator away. You get 0.93 according to the calculator. But how many sig figs should my answer have? Well, this says 3, right? And this says 3. So how many should my answer have instead of what's written? I know these numbers to 3 sig figs. So that means I must know this one to 3 sig figs as well. Which means I gotta add a 0 in there. So that would be the correct answer. I can do the same thing for water. And no, you don't have to write the formula every time. I'm just the instructor, and I'm doing this so that you have a record of, oh, where do those numbers come from? Oh, that's where it is. So there's my mass over volume for water. Obviously, those are the same number, so I'm going to get that as my density. We've actually sort of set up mass and density so that water is 1 gram per milliliter. Technically, at 4 Celsius, it's defined to be that. But at any other temperature, it's slightly less than that. It rounds up to 1, though. And again, 3 sig figs for all of these, so 3 sig figs. All of this is 3 sig figs. So is this one. So if I was going to put these in a column, and let's say that this is my column. I don't know, it looks like Italy got in an accident or something. Then this part of the column would be the water. And this part of the column would be the olive oil. There you go. So that's the basics of density. Let me know if you have any questions on that. Now, those are basic applications with density, such as, can I find the density of something? Yeah, if you know its mass and its volume. What if you knew the density of something and you wanted to find what mass is contained in a certain volume, or what volume is present with a certain amount of mass? That sort of thing. So then we can use density as a conversion factor. You can always just use it as the formula, D equals M over V, but it's probably more useful to remember that, oh, I can use it as a conversion factor, because then you can just drop it into any conversion that you want to. So let's try and do some problems using this sort of process. So let's suppose I have a glacier. And it's not a very big glacier if it's only 35,000 liters. Oops, oh no. Oh no. Hold on. There we go, I clicked on the wrong thing. Let's suppose I have this glacier here. What must the mass of the ice in the glacier be if this is the density? You know, we're just going to erase this hideous abomination. Alright, so I know that based on the problem statement, I know that the density of the ice is that. And I know that the volume of the ice is that. And I know that the temperature of the ice is 0 Celsius, but there's no temperature in the formula, so that's just extra information. That's not going to help you solve the problem. So how do I figure out the mass of the ice? I got dice and vice. How do I get mice? Now, you could just set up the formula and solve for m by saying, well, I'm going to just move this over here. And that will work. But what I'm going to show... Oops, excuse me. Gotta drink more water. What I'm going to show you is that we're going to inadvertently get this formula anyway by doing dimensional analysis. So if I take the volume of my water here, and I multiply it by the density because the volume is on the bottom here, this unit of volume could potentially cancel out with this if I were to make it match, right? So I got to turn liters into milliliters into centimeters cubed. And then I could cancel these centimeters cubed with these that I'm going to make. So let's do that. And once I've done that, so in a milliliter there are 10 to the minus 3 liters. That's on the slides in Unit 3. And 1 cubic centimeter is the same as a milliliter, which is shown in the unit on volume, which I think is also Unit 3. Now that I have the volume of this in cubic centimeters, which would just be whatever this result is if I typed it in the calculator, I can then multiply it by the density, and I'll end up with a mass. And the density of the water is just this, 0.9167, because that's what it said in the problem statement. So if I solve the problem now, I'll get an answer in grams. And the question didn't exactly tell us that we had to tell a mass in a specific unit. So you can just punch it all in your calculator. 35,720 times 0.9167 over 10 to the minus 3. That's the alphabet. There we go. And you get a ginormous number. 1, 2, 3, 4, 5, 6, 7. So 3.274 times 10 to the 367 grams. Or if you wanted to convert that into kilograms, I'm sure that by now you could do this conversion. Whichever of these you want to submit your answer as would be acceptable. So you can see that we multiplied by doing this. This was the volume, and this was the density. And so we effectively did the same thing as the formula. The formula might be easier for organizing your thoughts, but later on, we're going to use density to get from volume to mass in the middle of another calculation or two. And so this can be very useful to do. Yeah, this glacier would weigh about 32 metric tons. I mean, it's 35,000 1-liter bottles, so that's a lot of ice. Ice isn't exactly light. Because each 1-liter bottle would weigh about 1 kilogram. If you do 30,000 of them, then yeah. Yeah, that estimate checks out. Oh, I dropped my stylus, and I'm trying to pick it up with my feet, and that's not working. Let's do another problem here. Alright, how about this one? Air's got a density of 1.29 grams per liter. How much air do you need to have 32 kilograms of air? Whoop. There we go. We'll just scroll this down. Alright, so same deal. We know what the density is and we know what the mass is, but now this time we need to know what the volume is. So the density of air is 1.29 grams per liter, and the mass of air is 32.0 kilograms. And we need to figure out the volume of air. Now, whenever you're solving for volume in this sort of situation, you can actually get stuck in a mistake, we'll say. Because if I'm solving for this down here, a lot of people think, oh, I'm just going to move the m to the other side and then v's by itself, and that doesn't work. Because you'd actually get 1 over v. So what we have to do in order to solve for v here is you can't have it on the bottom when you solve for it. It's got to be on the top. So v needs to move over here by multiplying both sides by v. And then we need to divide both sides by d. And this will be the formula that we have. So when I do the dimensional analysis, it'll look like I'm taking the mass and dividing by the density, which is the same as multiplying by its reciprocal. So in other words, what my density up here is going to be, I'm going to have to flip this over, this number up here. Now, as we saw in the last problem, density can be used as a bridge from mass to volume and vice versa. Whatever I start with, I can use the density to convert it to the other thing. Well, in this question, I'm trying to find a volume, so I need to get my units to match up with the density unit that I'm starting with. So that means that I have kilograms to start. And I should probably turn it into grams, because then I can turn that into liters using the density. So let's do that. So there's my mass of air. I'm going to turn kilograms into grams. And then I'm going to turn grams into liters using the density. All my units cancel out, and that will leave me with a volume to solve the problem. My number goes on the bottom because that's where the grams are, right? So it's 1.29 grams per liter. So the per liter would be on the top. The 1.29 grams is on the bottom. And now you'll see that this is where that dividing by density thing comes in. So this was the mass, and this was dividing by density. So it looks just like the formula we used down here. And again, you can use the formula, but it's just good to get into the practice of doing the dimensional analysis and seeing how all the units cancel out. This is the previous problem, so let's just do that. So I'll punch that all in the calculator. 32 times 10 to the 3. Oops. Divided by 1.29. And I get that many liters, which if we consider sig figs is way too many, because this is 3 sig figs and this is 3 sig figs. So there you go. You would need 24,800 liters to get 32 kilograms of air. Oops. I meant to do that so that you could see the answer. All right, so the next slide, I'm going to give you some gold. And why my students don't just run off with the gold is beyond me, because the gold is expensive. Instead, we're going to do problems with it. So here you go. Oops, that's the title card, sorry. So here's the density of gold, 19.3 grams per cubic centimeter. If I had a gold bar with mass 329 grams, what volume in cubic centimeters would I get? Find the density of this carbonated beverage. That's pretty easy. And then finally, I'm going to make a ship. Here's its displacement, 65 times 10 to the 6 liters. Displacement is the volume of water that is pushed out of the way, or in other words, the volume of water that can be submerged. I want you to tell me the maximum amount of stuff in terms of mass that I can have on the boat and still have it float in water with density 1 gram per milliliter. Okay. Turns out ships actually have a maximum mass limit. You cannot go over that or the boat will submerge, because its density will be greater than that of the water around it. Now, fortunately, the seawater in the ocean is full of salt, which makes its density go up, and it gives you a lot more room to work with. Anyway, solve these 3 problems. We'll go over the answers in just a bit. Would you like to say something to the class? My cat just wanted to let you know good luck. We're all counting on you. gonna say something. Can you just rub the microphone? Yeah. 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 She really wants to say hi to you guys. Hi. Oh, now she wants to jump on my lap. That's not okay. I'm writing. I'm writing on the board. I'm gonna give you guys like 2 more minutes to finish up and type your answers in the chat, and then we'll go over the answers together with a cat. All right, I'm back. I'm done meowing at my cat. She's just sitting right next to me trying to jump in my lap. So I have to huddle close to the desk so that she doesn't actually do that, because she'll knock over everything if she does. Which is kind of just fair warning. If you hear everything falling apart and crashing over here, that's because my cat just tried to jump on my lap. Alright, so we know that the density of gold is 19.3 grams per cubic centimeter. And I know that its mass is... I should have just written it how I've been writing it before. Hold on. Is that. So what's the volume of gold? Now I want the answer in cubic centimeters, so if I turn grams into cubic centimeters using the density, then I can solve the problem right away. So we'll take the mass in grams, and I'm going to multiply it by the density conversion factor in such a way that the grams cancel out. So I need the grams to go on the bottom and the cubic centimeters to go on the top. And I just put in the numbers. And there you go. Oh, she finally left. That's good. So you should get 17.0 cubic centimeters. CC is a totally appropriate abbreviation for cubic centimeters. Some would say it's cromulent. Totally okay. Perfectly fine with that. All right, let's get the next one going here. This one invokes the definition of density. So all we're going to do is we're just going to use those numbers as written. Let me get rid of this here. Oops, that's not what I wanted. Undo. Boop. So for problem 2, we know that the mass of the beverage is 361 grams. I know that the volume of the beverage is 355 milliliters. And I know that the formula for density is just mass divided by volume. So let's do that. 361 over 355 grams per milliliter. And a 3 sig figs, I got 1.02. Now, it turns out that the density of a beverage is highly dependent upon how much sugar is in it. So if it's mostly water or just diet soda, the density is going to be very close to the density of water. But as you add more and more sugar, it gets more and more dense, because sugar is actually a very large molecule relative to water. So that's something that we'll actually encounter later on in 161. We're going to have you do a lab where you work with sugar solutions, presumably, if we could get you in the lab. And then finally, let's try and figure out how much stuff we can put on this boat. I have a hard time visualizing 65 times 10 to the 6 liters. Like, that's a lot of liters. Let me get this out of here real quick. You could just be up here. Select all. So I know that the volume of the ship is really big. That's disturbing when I read that, but also that's totally a thing that I would expect. There is a disturbing amount of sugar in soft drinks, which is why it could just be because I'm old, but like when I drink Sprite, which is really the only like soft drink that I drink, I put like 70 to 80% seltzer water, which is just carbonated water, and then the other 20% is Sprite because it's just too sweet for me. The density of our ship, in order for it to not sink, has to be less than 1 gram per milliliter. So what is the mass of the ship that I can have? Well, same as before, I have a volume in liters, and I can use density to go from milliliters to grams as long as I'm in milliliters. Now, I didn't request a specific mass for the ship, but being that it is a ship and not, like, say, a paperclip, kilograms is probably a good unit to be using for that. So I'm going to just solve for this in kilograms. So let's do the calculation here. So here's my volume, 65 times 10 to the 6 liters. We're going to turn liters into milliliters. We'll turn milliliters into grams using our maximum density requirement here. And I'll turn grams into kilograms. So that's how many liters are in a milliliter. This is the density of water. And this is how many grams are in a kilogram. Now you'll notice that, well, if I do it this way, this number and this number multiplied by each other just makes 1. So those cancel out immediately. You get 10 to the 0, which is 1. So I don't have to worry about those. And now I'm multiplying by 1, so I don't even need to get a calculator out of this. So 65 times 10 to the 6 kilograms. And if I move the decimal point over to make it actual proper scientific notation, that's the answer that I would get. That also works. I don't work in metric tons that much. However, that is a perfectly cromulent unit to use as well. If the only thing you learned today is that cromulent means perfectly fine, acceptable, whatever, then cool, I taught you a word. I'd rather you learn what density meant, but I'll settle for cromulent. All right, any questions about density? Those are some basic applications of density. On the worksheet, I have a few problems that use terms like, or problems like these, not terms like these. So yeah, make sure you do the worksheet and do the practice problems that I have recommended. Density is not going to be a huge part of the assessment that we do, but it is actually going to be the focus of an entire lab assignment that you're going to do next week. Okay, so we're going to come back to density and explore it in a lot more detail. Where am I at on time? Let's take a break because the temperature section isn't that long. So let me put the title card up for break time. Oops, that's if you went to lecture yesterday. We took a 5-minute break because I went over. So we'll do that. Actually, let's just take all the time. No, I'm just kidding. So we'll do that. I'll put the timer up. And I'll see you in 10 minutes. There's my timer. Alright, oops, hold on. I do not want to update the timer because it'll break everything. So I'm going to start that. I'm going to shut up and start playing more music from whatever this is that I was doing. So here, we'll just click somewhere. That's close enough, right? Okay. Man, I should have gone with the Super Mario Galaxy soundtrack because that was so much better quality. But I've only played bits and pieces of it, so I didn't really know any of the music except for that do track that randomly came on, and I was like, oh, I recognize this. That's that level I fell off of like 75 times. We're going to do a little brief discussion about temperature. Temperature is very straightforward. In fact, you are probably familiar with all of the temperature scales that we work with maybe one exception, and that would be Kelvin. Here are my 3 units of temperature conversion. On the left, you can see Fahrenheit. On the middle right is Celsius, and on the far right is Kelvin. We're going to ignore Kelvin for now, but we're going to talk about the important marks on these scales that we have defined. So right here at this blue line here, this is the freezing point of water. And so you can see that the numbers used for Celsius makes a little more sense than the one for Fahrenheit. Same thing for boiling water. A little easier on the Celsius side than it is for Fahrenheit. Fahrenheit starts at 32 for freezing and goes to 212 for boiling and has 180 gradations between them. Whereas Celsius starts at 0 and goes to 100 and has 100 gradations between them. So the interesting thing to note here is that 1.8 degrees Fahrenheit is equal to 1 degree Celsius. And these are exact numbers. But over here, you'll notice that this number, even though is weird, there's still only 100 gradations between them. So 1 Celsius and 1 Kelvin are exactly the same thing. That's kind of useful. Now, why are the numbers so weird for Kelvin? Well, first, actually, let's ask, why are the units so weird, or the numbers so weird for Fahrenheit? And the answer is, I don't know. I don't know what the 0 is for in Fahrenheit. Other than 0 is really, really cold. To be honest, the only thing that Fahrenheit is good for is confusing Canadians. So when you say, oh, it was 45 degrees today, every Canadian will go crazy because they're like, holy shit, how did you not die? I'm like, actually, it's really cold. Celsius is much more common in other places around the world, and we use it in the laboratory because, as we'll see, Celsius and Kelvin are going to be the important 2 temperatures that we work with, and that'll save us a conversion step. Now, the thing about Kelvin and why its number is so weird, this net 273.15 for 0, is that if we had a bottom of the temperature scale, we actually have numbers that we can assign there. So for Celsius, it's minus 273.15. And Fahrenheit, I forget what it is. It's like minus 450 or something like that. But Kelvin, we set the lowest temperature possible to what's called as absolute 0. Absolute 0 is the lowest definition of temperature that is possible based on what we define temperature as, which is the molecular movement of matter. At 0 degrees Kelvin, atoms and molecules do not translate, which means that they don't move around in space. They also don't rotate or vibrate. They are perfectly stationary. Now, if you are able to remove all of the vibrational, rotational, and translational energy from something, you would achieve this temperature. But obviously, that's impossible to do. Like, there's just so much ambient energy just everywhere around that getting to absolute 0 is impossible. So absolute 0 is a theoretical temperature. Now, absolute 0 is also known as what is called an absolute, or not absolute, but Kelvin is known as what's called an absolute scale. What that means is that it starts at 0 and goes up. The other temperatures here, Fahrenheit and Celsius, don't do that. They're relative scales. Now, Celsius and Kelvin are analogs of each other. They have the same value and the same dimensionality. And somebody already has mentioned this, so you kind of ruined my joke. There is another temperature scale that does the same thing with Fahrenheit, but we need to put a letter in for it. Can anyone tell me what letter should go there? And just in case my joke didn't translate well, here, we'll do this. There you go. What letter goes in the blank? No. Oh, my buzzer didn't go off because I had the... There we go. Oops. Someone said you wrong! There we go. I didn't have the screen highlighted, so... So it is R, and this is called the Rankin Scale. We will never use Rankin in this class, so... But the purpose of the Rankin Scale is that it is an absolute analog to Fahrenheit. So these two are linked together, and these two are linked together. But again, these two are the ones that we care about. And the other two can FERC off, we'll say. What are the formulas to get between Fahrenheit and Celsius? Because we don't want to deal with Fahrenheit in the lab, right? Fahrenheit is silly. So how do I convert between Fahrenheit and Celsius? Well, here's the formula that I use, and these conversion factors are exact. Now, what's important to note is that some formulas will write it like this. So degrees Fahrenheit equals degrees Celsius times 9/5 plus 32. And then the reverse would be this. So Fahrenheit minus 32. And then times 5/9. You'll notice that 9 divided by 5 is just 1.8. And then the reciprocal of 9/5 is 5/9. Which is the same as dividing by 1.8. So I wrote these formulas because it's easier to typeset 1.8 instead of 9/5. But if you see these fractional formulas, they also work. You can use any formula you want to on the screen to turn from Fahrenheit to Celsius. Now, to get between Celsius and Kelvin, we have a different formula. But this value right here is not exact. This actually keeps going. It's like 273.1451 something. I don't know. So this value right here is approximate. And what that means is that if you're going between Celsius and Kelvin, you're only going to get enough sig figs based on how many decimals your answer goes in, because it's an addition problem. You're also limited to how many digits you use for the Kelvin formula. So if you use 273.15, you can only go down to the hundredths place with your answer. If you use 0.145, then you can go down to the thousandths place, and so on. But these are approximate. Up here on the top, everything up here is exact, which means the number of sig figs you put in should be the number of sig figs you get out, unless you're doing addition at the end with this 32. And that could add another sig fig. So these are combined operations, and you got to be careful with them. So those are the formulas for temperature. You can also just go online and type in, like Google, like, hey, what's 88 Fahrenheit in Celsius? And it'll do that. I would recommend that you, for our exercises, use the formulas to do temperature so that you get the correct number of sig figs, because I think Google will just print out all of the zeros and nines and whatever that it wants to. Because I know on the quiz, when you do the quiz for this unit, there's going to be some questions that ask you, what's this temperature in this scale? And you'll have to do the conversion. And if you type it in Google and it gives you too many sig figs and you type it in the wrong answer, you're going to not get your point for that question. So make sure you're able to do the sig figs in the formulas. I already talked about absolute zero. Absolute zero, again, is the absence of molecular motion. We define that as 0 Kelvin, and all temperatures go above that. You cannot go below absolute zero, so you can't have negative Kelvin, at least in terms of that scale. If you are very, very curious, you can actually look at the definition of temperature using entropy and enthalpy. And based on that definition, you can actually get negative Kelvin, which is the hottest temperature possible, which is like, wait, what? So if I go past absolute zero, it's even hotter? And the answer is yeah, because temperature is defined using thermodynamics, and it's weird. So if you look this up later and you're like, wait, negative Kelvin exists. Yeah, it does. But for our purposes in this class, we can't do that. You cannot go below 0 Kelvin from the positive side. That might be it. That might all be all the slides I have. Oh, it's just this. Oops, hold on. So go ahead and convert these temperatures into the requested unit. So turn Kelvin to Celsius, etc. This will get you some practice in figuring out like what these numbers mean. Like, is 175 Kelvin hot or cold? Like, what is that? Is 47 Celsius hot or cold? And by converting these, you can actually start to get the idea of what these are. Okay, so go ahead and do that, and we'll go over the answers in about 5 minutes. I'll see you for that. Meow. Press next out of the class. My cat came back. Just in case you aren't looking at the chat, I had a student email asking for the Discord link. If someone has that handy and can paste it in the chat, I will send it to that student. And I'm sure that they would appreciate it. So if you can do that, go ahead and do that. Otherwise, go back to work on the problems. All right, let's go over the answers here. I could actually write directly on these slides. Where'd my stylus go? I knocked over my stylus because the cat ran through my headset and my stylus went flying, so I had to go find it, which is why that took so long. So we're going to convert Kelvin into Celsius. So the formula is Kelvin equals 273.145 plus whatever our temperature is in degrees Celsius. So if my temperature in Kelvin is 175, that means that I have this expression. So in order to figure out what the temperature is in Celsius, I would just subtract. So I'd do 175 minus 273.145. We'll get rid of that. Now, obviously, when I'm doing my subtraction like this, my subtraction is going to go to the ones place. And then I just had to invert it. I have a calculator here, so I'm just going to do it this way. And so I get 98.145, which again is going to get rounded to that. So that temperature in Kelvin must be that temperature in Celsius. All right, let's get rid of all this. Maybe this would have been easier to do on the Photoshop, but that's okay. I've made this bed, now I must lie in it. All right, 47 Celsius to Fahrenheit. So Celsius to Fahrenheit is Fahrenheit equals 3 Celsius times... I'm trying to remember the formulas, and it's not really working because I don't memorize these formulas because that's dumb. So hold on, let's go back and get the formulas real quick. It is times 9 over 5, so I had the right idea. Sorry. And so our Celsius temperature is 47 times 9 over 5 plus 32. The result of that calculation is going to be 84.6, which becomes 85 for 2 sig figs. And then I add 32 to it. Oops, not 116, 117. And holy crap, is that hot. Don't go outside if it's 117 Fahrenheit. Like that would be extremely bad. All right. The next one is rather cold. We don't want to go outside when it's negative 11 Fahrenheit either. And so we'll do the reverse formula, which is degrees Celsius equals Fahrenheit minus 32 times 5 over 9. So that becomes negative 11 minus negative 30 or minus 32, which together is minus 43. Yeah, that's submerging yourself in water, which you can get out of. Submerging yourself in air is a little different. Also, there's a hell of a difference between 40 Celsius and 47 for the human body. We'll multiply these together. Not 59, 5/9. So I got that. Since this number has 2 sig figs in it, my answer should also have 2 sig figs. Here's a bit of trivia. There is a point on the scale where Fahrenheit and Celsius are the exact same thing. Like one converts to the other and it's the same value. Anybody know what that is without looking it up? This is a question on Who Wants to Be a Millionaire years ago, and like I think I was in like elementary or high school at the time. I was like, "Oh, I know that," because we had a thermometer outside, and I had looked at it and noticed, "Oh, they're the same number right there." Would the second one be 2 sig figs? No, because when you add 80 whatever it was to 32, you get a 3 sig fig number. Remember, you were doing a combined operation here. You're doing addition and multiplication, which means that you need to consider the rules as you go to the next step. So, number 2 is definitely 3 sig figs, even though the number that you put in only had 2, because you're doing addition. Oh yeah, put that Discord link in here if you can, for me. I have a student who's been trying to find them in the video archives, and I certainly can't blame them for having a difficult time doing that, because if you're just like tabbing through it, you're basically just like shooting an arrow at a target that's 500 feet away and hoping for the best. 79 Celsius to Kelvin. So Kelvin is Celsius plus 273.145. Well, my Celsius is 79. Oh, that's right. Send me an email. It probably thinks that it's spam. Just email it to me and I will get it to that student. That's probably why the student couldn't find it in the first place, because I don't remember what lecture I did that for. What's 273 plus 79? 352. And this is only going to the ones place because the number that I started with goes to the ones place. 373 Kelvin to Fahrenheit. That's really obnoxious, unfortunately, but we'll have to do it. So, again, Kelvin equals Celsius plus 273.145. So I'm just going to move that to the other side, and you'll get this. Okay, cool. Yeah, I'll make a note of that just to have it on record. Or you know what I can do? I just take the email that the student sent me if I could find it and just save it as a task for whoever needs it. I'll also go post it as an announcement around the discussion board or something like that. So there's my Celsius temperature. Now I can turn that into Fahrenheit by taking Celsius. Oops, that's not a degree symbol. Degrees Celsius times 9/5 plus 32. And it's 100 Celsius, so when I put this in the formula, I should get 212, right? 100 times 9/5 should be 180 plus 32 is 212. There you go. All right, so that's how we do conversions with temperatures and using the correct number of sig figs, okay? So again, be very careful. This is another one of those instances where addition and multiplication occur in the same time when you're doing the Fahrenheit Celsius thing. And that can cause you to gain or lose sig figs depending on which direction you're going. Okay? Not the answer to how many sig figs is not always, oh, how many did we start with? Because when you add or subtract, that can change. So just be aware of that. There we go. We can celebrate now. There you go. 2 units at once. Feels good. Okay, thanks. What time is it? What do we got? It is 3:30, so we have 25-ish minutes left. My cat is really excited that we are done earlier, I guess, because now he's going to sit there and meow at me. If you want to talk about anything else, such as like more Q&A stuff that we did yesterday, we could do that for 20 minutes. Otherwise, that's all I have for today. We're not going to start Unit 6. But what I will say is that Unit 6 is finally chemistry. Like, if you've been wondering, like, what the hell class am I taking? Like, we haven't done a single chemistry-related thing yet. And, yeah, that's true. We're going to start that on Tuesday. Kresnik, please. I'm giving a lecture. He's sitting there just yowling at the ceiling, swinging his head around like, oh, I'm so lonely. Why won't anyone pay attention to me? Because I'm teaching. Now he's staring at me. I made fun of you on the internet, cat. Oh, he's mad now. My mic isn't that sensitive. I'm sure that you're not picking him up, but I can hear him through my headset. So. So if you have any questions, let me know. I'm going to get that link and send that to that student. Oh, you can hear him. Oh, okay. Yeah, he's the loud one. Maya's the one that just kind of goes in the mic. Oh, I have to uncheck this before. There we go. And then this is the student that wanted it. And that's done. Okay, cool. Yeah, he's either lonely or I need to give him more food, but I literally just fed him 2 hours ago. I can't imagine that they ate that much food that quick. Other announcements to make. Tonight is the soft deadline for lab number 1. Again, that is a soft deadline, so if you can get it in by midnight, please do. I will announce last call tomorrow on Friday, and then I will download all of the labs. And once I have them, then you have to use your NQA if you want to turn in stuff late. So make sure that you are working on that and that you get it uploaded. Make sure it's an XLSX file. Make sure you follow the naming conventions. And make sure you ask me any questions tonight if you need them, because tonight's kind of the last chance to do that. Okay, I'm going to put this screen up. I guess we're done here for today. So have a wonderful afternoon, and enjoy the rest of your weekend. Remember to do quiz number 2 on Monday. That'll be Unit 3. And then the next quiz that we're going to have, which I should post on Monday, will be Units 4, 5, and 6, which are all really short, but it should be one of the easier quizzes of the 3 that you've taken. Have a wonderful weekend, and I will see you on Tuesday.